In this video, we're going to be looking at integer exponents and how do you evaluate expressions containing zero or negative exponents. To accomplish this, we're going to look at what kind of pattern occurs when we're looking at exponents. We know 2 squared is 4, and 2 cubed is 8, 2 to the 4th is 16, and 2 to the 5th is 32, because it's 2 times 2 times 2 times however many is in the exponent. But if I track it backwards, I see that a constant dividing by 2. So 4 divided by 2 is 2, 2 divided by 2 is 1, then 1/2, then 1/4, which is the same as 1 over 2 squared, 1/8, and 1/16, or 1 over 3 squared. We see that this is just following the pattern of dividing by 2. That can give us a special note that b to the negative e is the same as 1 over b to the e. So the negative exponent moves that number into the denominator, making the exponent positive. We can do the same thing with the number 4 to exponents. 4 to the first power we've seen is 4. 4 squared is 16. But what about in the middle of that? What about 4 to the 1/2 power? 4 to the 1/2 power is the same as the square root of 4, and the square root of 4 is 2. So between 4 to the first power and 4 to the second power is 4 to the 3 over 2 power, or the square root of 4 cubed. And if we do 4 times 4 times 4, we get 64, and the square root of 64 is 8. At that point, I can notice some interesting correlations. 2 to the first power is 2. 4 to the 1/2 power is 2. That means if I had to write the number 2 as an exponent, I can write it as 2 to the first power or 4 to the 1/2 power. Similarly, 8 is 3 cubed or 4 to the 3/2 power. What does this mean about following the pattern with other numbers? We can follow the pattern down and fill in the exponent values like negative 1/2 and negative 3 over 2, negative 5 over 2. Looking at these and looking at the values from above, I can see that 4 to the negative 1/2 power is the same as 4 to the 1/2 power in the denominator, or 1/2. 4 to the negative 1 is 1 over 4. 4 to the negative 3 over 2 is 1/8 because it is 1 over the square root of 4 to the 3rd power, which we saw earlier. The square root of 4 to the 3rd power is 8. So these things are very directly related. We can extend these patterns on the 4 to the powers, but let's take a look at what happens with the 8s. 8 to the 0 is 1, and 8 to the 1 is 8. But I have a 1/3, 1/2, and 2/3 in between them. I see that if a 1/2 power means square root, then 1/3 power means cube root, and the cube root of 8 is 2. The 1/2 power of 8 is the square root of 8, which is 2 times 2 times 2, so 2's come out and a 2 stays in, giving me 2 square root of 2 as my simplified solution. 8 to the 2/3 power can be looked at as both the cube root of 8 squared, but you can also look at the 8 to the 1/3 power, which is 2, and square that to get the number 4. We could extend that pattern down through the 8s to the powers just by looking at the positive powers and putting them in the denominator of a fraction following that pattern. So a good keynote about a base raised to a fractional exponent, a base to the power of n over d, is the d root of b to the n. We've been able to see through the pattern that any number to the 0 power is 1, but we haven't seen it for 0. This does not work if it is 0. We have 3 steps to simplifying exponents. The first is to expand them entirely, then to eliminate what they have in common, and then finally to simplify these into one expression. The formal name of an exponent is the indices, or the index, and the formal name for a square root is a surd. We will be using the 3 steps to simplify an integer exponent in our next lessons. Remember, math is the only subject in school that you can and should check your work for every question on a test.